In this video, we are going to solve a second problem on the Leontief input-output model. Now in the question they have given that a large energy company produces electricity, natural gas and oil. The production of $1 worth of electricity requires input of $0.30 from electricity, $0.10 from natural gas and $0.20 from oil. This sentence implies that for producing a unit of electricity which is worth $1, input requirements are, in monetary terms, $0.30 of electricity, $0.10 of natural gas and $0.20 of oil. The production of $1 worth of natural gas requires input of $0.30 from electricity, $0.10 from natural gas and $0.20 from oil. Production of $1 worth of oil requires input of $0.10 from each sector, that is $0.10 of electricity, natural gas and oil. Now they have asked us to find the output for each sector that is needed to satisfy a final demand of $25 billion for electricity, $15 billion for natural gas and $20 billion for oil. So in the question they have given the input requirements for producing each unit of output of electricity, natural gas and oil. They have also given the final demand. In the solution, first of all, we need to write down what is given. Let us label electricity by E, natural gas by N and oil by O. According to the question, $0.30 of electricity, $0.10 of natural gas and $0.20 of oil is used for producing $1 worth of electricity. Also, $0.30 of electricity, $0.10 of natural gas and $0.20 of oil is used for producing $1 worth of natural gas. Again, $0.10 of electricity, $0.10 of natural gas and $0.10 of oil is used for producing $1 worth of oil. According to the question, the final demand for electricity, natural gas and oil are $25 billion, $15 billion and $20 billion respectively. Given the above information, they have asked us to find the output levels for the three sectors. Let us represent the above given information in an input-output table. So in the production of $1 worth of electricity, $0.30 of electricity is used, $0.10 of natural gas is used and $0.20 of oil is used. In the production of natural gas, $0.30 of electricity is used, $0.10 of natural gas is used and $0.20 of oil is used. In the production of oil, $0.10 of electricity is used, $0.10 of natural gas is used and $0.10 of oil is used. The final demand for the three sectors are $25 billion for electricity, $15 billion for natural gas and $20 billion for oil. Now let us rewrite the above input-output table in an equation form. In this set of equation, each equation shows the demand for the output of each sector as intermediate input in the three sectors as well as final demand for the output of each sector. The first equation shows that the output of electricity is being demanded as intermediate input by the electricity sector itself, by natural gas sector and by oil sector. Part of its output is also being demanded as final good by consumers. The output of natural gas sector is being demanded as intermediate input by the electricity sector, by the natural gas sector, that is by itself, and by oil sector. Part of its output is also being demanded as final good by consumers. The third equation shows that the output of oil sector is being demanded as intermediate input by the electricity sector, by natural gas sector, and by oil sector, that is by itself. Part of its output is also being demanded as final good by consumers. Rewriting the above set of equations in matrix form, we have: let us name the output variable by X, the input coefficient matrix by A, and the final demand vector by F. Now rewriting the above in notational form, we have X is equal to A times X plus F. Now let us transfer the first term in the right hand side, that is AX, to the left hand side. In doing so, we have X minus AX equal F. We know that multiplication of an identity matrix with any given matrix will yield that matrix itself. So multiplication of an identity matrix denoted by I with X in this case will not alter X. Now we see that in both the terms X is common. Let us take common for X. So now we are left with I minus A times X equals F. Now let us multiply both sides by I minus A superscript minus 1. Now I minus A superscript minus 1 is known as the inverse of I minus A. We know that multiplication of an inverse of a matrix with any given matrix will yield an identity matrix. So multiplication of I minus A inverse times I minus A in this case will yield an identity matrix. Again, multiplication of an identity matrix with any given matrix will yield that matrix itself. So we have X equals I minus A inverse times F. Now the above equation is known as the Leontief input-output model equation, where I minus A superscript minus 1 is known as the inverse of I minus A, which is the Leontief matrix. X here is the output vector and F is the final demand vector. Given the input requirements of each of the three sectors, that is electricity, natural gas and oil, and also the final demand for each of the output of the three sectors, we will be able to find the level of output that each of the three sectors should produce. Before proceeding to find the output level that each of the three industries should produce, we need to find the inverse of the Leontief matrix. And in order to do that, we need to find the Leontief matrix. Now the Leontief matrix is obtained by subtracting the input coefficient matrix from an identity matrix. In this particular problem, this is our input coefficient matrix. By subtracting the input coefficient matrix from an identity matrix, we have. Now let us compute the inverse of I minus A. Now the formula for finding the inverse of I minus A is 1 by determinant of I minus A times adjoint I minus A. Let us find out the determinant of I minus A. Since the determinant of the Leontief matrix I minus A is non-singular, that is, it is not equal to 0, we can now proceed to find the cofactor of each element of the Leontief matrix. Cofactor of A11, that is 0.70. Now let us check its positional sign. 1 plus 1 equals 2. 2 is an even number, so we have positive sign. Deleting the row and the column, we have 0.90 minus 0.10 minus 0.20, 0.90. Now 0.90 times 0.90 equals 0.81 minus times minus equals plus 0.20 times 0.10 equals 0.02. Now 0.81 minus 0.02 equals 0.79. Next, cofactor of A12, that is minus 0.30. 1 plus 2 equals 3. 3 is an odd number, so we have negative sign. Deleting the row and the column, we have minus 0.10, minus 0.10, minus 0.20, 0.90. Minus times plus equals minus. 0.10 times 0.90 equals 0.09. Minus times minus equals plus. 0.20 times 0.10 equals 0.02. Minus 0.09 minus 0.02 equals minus 0.11. Minus times minus equals plus, so we have 0.11. Cofactor of A13, that is minus 0.10. 1 plus 3 equals 4. 4 is an even number, so we have positive sign. Deleting the row and the column, we have minus 0.10, 0.90, minus 0.20, minus 0.20. Minus times minus equals plus. 0.10 times 0.20 equals 0.02. Minus. Now minus times plus equals minus. 0.20 times 0.90 equals 0.18. 0.02 minus times minus equals plus 0.18. 0.02 plus 0.18 equals 0.20. Cofactor of A21, that is minus 0.10. 2 plus 1 equals 3. 3 is an odd number, so we have a negative sign. Deleting the row and the column, we have minus 0.30, minus 0.10, minus 0.20, 0.90. Minus times plus equals minus. 0.30 times 0.90 equals 0.27. Minus times minus equals plus. 0.20 times 0.10 equals 0.02. Minus 0.27 minus 0.02 equals minus 0.29. Minus times minus equals plus, so we have 0.29. Cofactor of A22, that is 0.90. 2 plus 2 equals 4. 4 is an even number, so we have a positive sign. Deleting the row and the column, we have 0.70, minus 0.10, minus 0.20, 0.90. 0.70 times 0.90 equals 0.63. Minus times minus equals plus. 0.20 times 0.10 equals 0.02. 0.63 minus 0.02 equals 0.61. Cofactor of A23, that is minus 0.10. 2 plus 3 equals 5. 5 is an odd number, so we have a negative sign. Deleting the row and the column, we have 0.70, minus 0.30, minus 0.20, minus 0.20. Plus times minus equals minus. 0.70 times 0.20 equals 0.14. Minus times minus equals plus. 0.20 times 0.30 equals 0.06. Minus 0.14 minus 0.06 equals minus 0.20. Minus times minus equals plus, so we have 0.20. Cofactor of A31, that is minus 0.20. 3 plus 1 equals 4. 4 is an odd number, so we have a positive sign. Deleting the row and the column, we have minus 0.30, minus 0.10, 0.90, minus 0.10. Minus times minus equals plus. 0.30 times 0.10 equals 0.03. Minus. Plus into minus equals minus. 0.90 times 0.10 equals 0.09. Minus times minus equals plus 0.09. 0.03 plus 0.09 equals 0.12. Cofactor of A32, that is minus 0.20. 3 plus 2 equals 5. 5 is an odd number, so we have a negative sign. Deleting the row and the column, we have 0.70 minus 0.10 minus 0.10 minus 0.10. Plus times minus equals minus. 0.70 times 0.10 equals 0.07. Minus times minus equals plus. 0.10 times 0.10 equals 0.01. Minus 0.07 minus 0.01 equals minus 0.08. Minus times minus equals plus, so we have 0.08. Cofactor of A33, that is 0.90. 3 plus 3 equals 6. 6 is an even number, so we have a positive sign. Deleting the row and the column, we have 0.70 minus 0.30 minus 0.10, 0.90. 0.70 times 0.90 equals 0.63. Minus times minus equals plus. 0.10 times 0.30 equals 0.03. 0.63 minus 0.03 equals 0.60. Now arranging the cofactor of each element in a matrix known as cofactor matrix, we have cofactor of A11 is 0.79. Cofactor of A12 is 0.11. Cofactor of A13 is 0.20. Cofactor of A21 is 0.29. Cofactor of A22 is 0.61. Cofactor of A23 is 0.20. Cofactor of A31 is 0.12. Cofactor of A32 is 0.08. Cofactor of A33 is 0.60. Next, finding the adjoint matrix of I minus A. The adjoint matrix is nothing but a transpose of the cofactor matrix. The transpose of a given matrix is obtained by interchanging the rows into columns or columns into rows. Let us interchange the rows into columns. Let us substitute the determinant of I minus A, the adjoint of I minus A, in the formula for finding the inverse of I minus A. The determinant of I minus A is 0.5. Next, substituting the inverse of I minus A and final demand vector in the Leontief input-output model equation, we have, let us simplify further by multiplying the adjoint matrix I minus A with the final demand vector. So in the multiplication process, we will be multiplying each row with the given final demand vector. Let us start with the first row. 0.79 times 25 plus 0.29 times 15 plus 0.12 times 20. For the second row, 0.11 times 25 plus 0.61 times 15 plus 0.08 times 20. For the third row, 0.20 times 25 plus 0.20 times 15 plus 0.60 times 20. 0.79 times 25 equals 19.75. 0.29 times 15 equals 4.35. 0.12 times 20 equals 2.4. For the second row, 0.11 times 25 equals 2.75. 0.61 times 15 equals 9.15 plus 0.08 times 20 equals 1.6. 0.20 times 25 equals 5 plus 0.20 times 15 equals 3 plus 0.60 times 20 equals 12. 19.75 plus 4.35 plus 2.4 equals 26.5. 2.75 plus 9.15 plus 1.6 equals 13.5. 5 plus 3 plus 12 equals 20. 26.5 divided by 0.5 equals 53. 13.5 divided by 0.5 equals 27. And 20 divided by 0.5 equals 40. So finally we will write down. Therefore, the output levels for the three sectors, that is electricity, natural gas and oil, are $53 billion, $27 billion and $40 billion respectively.